In the last lecture, we were discussing natural convection. Okay. I told you that when there is a heated object placed in a colder fluid, the heat transfer from the object results in an increase in the temperature of the fluid close to the object. Because hotter fluid is usually lighter, it has a lower density, due to which there is a buoyancy force in the direction opposite to gravity, which leads to the rising of the hotter fluid, and there is colder fluid from the ambient that enters in to replace the hot fluid, and this acts as a mechanism for convecting heat away from the surface. And this mechanism, as we saw when we discussed dimensional analysis, could be significantly more efficient than the mechanism of heat conduction. So, here I will not do analytical calculations for the correlations for natural convection. I will just write down the governing equations and scale them and determine the form of the correlations for heat transfer due to natural convection. So, the configuration was an object of characteristic dimension Lc in a fluid with temperature T infinity far away. Okay. In a fluid with temperature T infinity and density rho infinity far away. Okay. The temperature at the surface of the object was T 0, and we wanted to find out what is the rate of natural convection. So, here the velocity is actually generated by the fluid flow. Okay. Here the velocity itself is generated due to the fluid flow. I am sorry, the velocity is generated due to the buoyancy force, and the buoyancy force in turn is due to temperature difference. That temperature difference is determined from the energy balance, and also entering into the energy balance is the flow velocity, which convects the energy. So, the conservation equations that we considered were the mass, momentum and energy equations. The one simplification that we had made here was from the momentum equation, okay, from the complete momentum equation. In the presence of a temperature variation, we had neglected out the momentum equation in the absence of temperature variation for the static pressure. Okay. When there is no temperature variation, there is no velocity, and in the absence of velocity, there is still a pressure gradient due to the gravitational force on the fluid. Okay. In the absence of temperature variations, the density everywhere is equal to rho infinity. Okay. So, therefore, you get this equation for the static pressure, and we had subtracted out the equation for the static pressure to get a momentum equation which depends only upon the difference in density between the object and the ambient fluid, okay, as it is necessary. Okay. There should be no driving force if the density is equal to the ambient density. Okay. So, only when there is a variation in density, only then there is a driving force, okay, for the in the momentum conservation equation. This driving force in the momentum conservation equation generates a velocity field. That velocity field, through the convective term in the energy balance equation, convects the heat away, okay, and this results in natural convection. So, we had discussed the Boussinesq approximation, the approximations that are made in the governing equations. First, the variation in density is a linear function of the variation in temperature. Okay. The variation in density is a linear function of the variation in temperature. Note that in normal fluids, when the temperature is higher, the density is lower. Okay. Therefore, beta is usually a negative constant. Okay, beta is usually a negative constant. In some cases, the change in density is written as minus rho infinity into beta into T minus T infinity. Okay. In that case, beta is a positive constant, okay, but the way I have written it here, beta is a negative constant, okay, which basically tells you how much the fractional variation in density due to the variation in temperature. And because beta is a negative constant, the buoyancy force here acts in the direction opposite to gravity. Okay. So, if gravity is downwards, because beta is a negative constant, the buoyancy force is upwards. Okay. Density is considered a constant in the mass conservation equation and the convective terms in the momentum conservation equation. So, the mass conservation equation is identical to what we have for an incompressible fluid flow. Okay. The mass conservation equation is identical to that for an incompressible flow. Okay. The momentum conservation equation also identical to that for an incompressible flow, with the exception that there is an additional term due to buoyancy here. Okay. This additional term due to buoyancy is present in this conservation equation, which contains in it density variations. Okay. And we get the energy balance equation also for a fluid with constant thermal diffusivity. Okay. The energy balance equation is written for a fluid with constant thermal diffusivity. And I discussed conditions under which this is valid. For an ideal gas, the density is inversely proportional to the absolute temperature. The viscosity and thermal conductivity are proportional to T to the half, where T is the absolute temperature. And therefore, the Boussinesq approximation is valid when the difference in temperature between the object and the ambient is much smaller than the absolute temperature in Kelvin. Okay. So, under those conditions, the Boussinesq equations can be used. We considered the case of liquid water between 20 degrees centigrade and 60 degrees centigrade, and there I had shown you that the variations in the density and the specific heat are actually very small. Okay. This data was obtained from tables. The variation in the density and the specific heat are actually very small. Okay. There is some variation in the thermal conductivity, but there is a still larger variation in the viscosity, due to which we strictly cannot use the Boussinesq approximation in this particular case. Okay. If the temperature difference were smaller, then we could have used the Boussinesq approximation. Okay. So, let me write down the equations again. Okay. These are called the Boussinesq equations. Divergence of the velocity is equal to 0. Okay. V dot grad V is equal to rho infinity into that is equal to minus the divergence of the dynamical pressure. Okay. Note that we have subtracted out the static pressure in this case, plus mu times the Laplacian of the velocity. Okay. Plus I substitute for the buoyancy force as rho infinity beta into T minus T infinity into the gravitational acceleration vector. Okay. And the thermal conductivity equation is V dot grad T is equal to the thermal diffusivity far from the object times del square T, okay, where I have neglected the change in the thermal conductivity with temperature or with position in this case. Okay. There will be a change in viscosity, thermal conductivity and density with position, because the temperature is changing as a function of position. Okay. Okay. So, we can scale these equations. Okay. The natural length scale for the position vector is the characteristic length of the object. Okay. And since the gradient has dimensions of inverse distance, okay, the scaled gradient can be written as LC times grad, okay, where gradient has components partial by partial x, partial by partial y and partial by partial z in 3 dimensions, and you scale each of those x, y and z. Unit vectors are dimensionless. Okay. The velocity will be scaled by a characteristic velocity which we do not yet know, okay, The scale temperature T star is equal to T minus T infinity by T naught minus T infinity. Okay. The usual scaling, because T star has to be 1 at the surface and it has to be 0 far from the surface. And I will use a scaling for the gravitational field, okay, is equal to the velocity by the magnitude, okay, by the magnitude of the gravitational acceleration. Okay. The gravitational acceleration on the Earth's surface is approximately 10 meters square per second. So, the gravity vector which is acting in the vertical direction, that is being scaled by its magnitude. Okay. And the dynamical pressure can be scaled either by inertial or viscous scales. I will scale it here by the inertial scale. Okay. I will scale this here by the inertial scale. Okay. So, these are the scaled coordinates, the velocity. Note that this velocity scaling we do not yet know. Okay. So, we have to substitute this into the equation in order to find out what is the scaling for the velocity. Okay. So, the scaled equations, mass conservation equation, del dot V equals 0. Okay. The divergence of the velocity is equal to 0, that is a mass conservation equation. Okay. The momentum conservation equation, okay, rho infinity V c square by L c V dot grad V. Okay. The Laplacian has dimensions of 1 over length square. Okay. The Laplacian has dimensions of 1 over length square. Okay. Where this g star vector is a unit vector in the direction of gravity, because it has unit magnitude, okay, and g is the gravitational acceleration. Okay. So, that is the equation. Okay. And you can scale either by the inertial or the viscous terms. In this case, I will scale by the inertial term, because I know that in the end the inertial term is going to be dominant. Okay. So, therefore, I divide throughout by this term. Okay. I divide the momentum conservation equation throughout by this term, okay, and I will get V dot grad V is equal to, there should be a minus sign here. Okay. There should be a star here. Okay. So, that is the momentum conservation equation. Okay. For the inertial terms and the buoyancy force to be of equal magnitude, this coefficient has to be 1. Okay. Because the inertial the buoyancy force is what is driving the flow, and the flow has to be driven either by the buoyancy force has to be balanced either by the inertial term or by the viscous term. In this particular case, we have chosen the inertial term to balance the buoyancy force. We will see that that is actually a valid assumption soon. Okay. but for the inertial term to balance the buoyancy force, that term in the red outline has to be order 1, which implies that V c has to be equal to square root of beta g into t minus t infinity times L c. Okay. That has to be the characteristic dimension. Okay. And if that is the case, I can substitute that in here and get V star dot grad plus note that this is a dimensionless group. Okay, this is a dimensionless group which is defined based upon the characteristic velocity and the characteristic length. Okay, it is an inverse of a Reynolds number. Okay. Traditionally, the Grashof number is defined as the square of this Reynolds number. Okay, rho infinity square beta g t naught. Okay, this should be T naught, my apologies, okay, because this is T naught here. Okay. So, the Grashof number is the square of the Reynolds number based upon the characteristic velocity and the characteristic length scale. Okay. I can also write this as beta g into T naught minus T infinity L c cubed by nu infinity square, where nu infinity is the kinematic viscosity based upon the temperature of the ambient fluid. Okay, so, that is the Grashof number. So, based upon the Grashof number, this equation can be written as the Grashof number to the minus half power del square V plus T times G. Okay. So, that is a scaled momentum conservation equation. Okay. And finally, we have the scaled energy balance equation. Okay. Finally, we have the scaled energy balance equation. Okay. V dot grad T is equal to alpha infinity del square T. Okay. Substituting the equations, the characteristic velocity times T naught minus T infinity by L c into V dot grad T in scaled quantities is equal to alpha by L c square into T naught minus T infinity del star square T star. Okay. And these two will cancel out. Therefore, we get V star dot the grad of T is equal to alpha by alpha infinity V c L c. Okay. This can also be written as alpha infinity by nu infinity kinematic viscosity nu infinity by Vc Lc alpha infinity by nu infinity, ratio of kinematic viscosity, I am sorry, ratio of thermal diffusivity and momentum diffusivity is the inverse of the Prandtl number, okay, is the inverse of the Prandtl number. Prandtl number is momentum by thermal diffusivity, okay. So, thermal by momentum is inverse of the Prandtl number, okay. So, this is equal to 1 by the Prandtl number. Nu by VL is 1 over the Reynolds number, and as I told you earlier, this is equal to 1 over the Grashof number to the half, okay. Okay. So, this is the energy balance equation. Okay. So, this is the energy balance equation. So, let me write down once again what are the mass, momentum and energy balance equations in scaled form. Okay. Okay, that is the momentum, that is the mass conservation equation. Momentum conservation equation is so, this is the momentum conservation equation. Okay. So, this contains two parameters, the Grashof number and the Prandtl number. Okay. Now, there is another dimensionless group that is sometimes used, which is called the Rayleigh number. Okay. Okay, which is equal to G beta into by nu infinity times the thermal diffusivity, okay, which will basically be equal to the Grashof number times the Prandtl number, okay, because Prandtl number is nu infinity by alpha infinity, okay. Yeah, that is correct. Okay. Okay, so that is the other dimensionless group that is sometimes used, and there is one relation that relates the three parameters, the Grashof number, the Prandtl number and the Rayleigh number. Okay. Now, in our discussion of dimensionless groups and correlations, if you recall, we had actually evaluated numerically what is the Grashof number, and the Grashof number ranges typically in the range 10 power 4 less than equal to the Grashof number less than or equal to 10 power 9. Okay. It could go even higher if the temperature difference is even larger, but normally it is in this range. Okay. This we had done when we had examined dimensionless groups and correlations. We had actually evaluated the magnitude of the Grashof number, okay, and this is very large. Okay. So, this implies that this is basically like a high Reynolds number flow. Okay. When the Reynolds number is large, inertial effects are dominant compared to viscous effects. Okay. If you recall from boundary layer theory, okay, when the Reynolds number is large, inertial effects are dominant compared to viscous effects. However, viscous effects and similarly when the Peclet number is large or the Prandtl number times the Grashof number is large, okay, convective effects are dominant compared to diffusive effects. However, if you neglect diffusion altogether, the equation reduces from a second order differential equation to a 0th order differential equation in the cross stream direction, and therefore you cannot satisfy boundary conditions. Physically, if diffusion is neglected, there is no transport from the surface, because transport perpendicular to the surface has to take place due to diffusion. If diffusion is neglected, there is no transport perpendicular to the surface, and because of that there is no heat flux from the surface, and therefore there is no temperature variation in the fluid. Similarly, there is no momentum transport from the surface, and therefore you cannot satisfy the no slip condition. In such cases, when the Grashof number is large, it is necessary to postulate the presence of a boundary layer whose thickness goes to 0 as the Grashof number goes to infinity, in such a way that there is a balance between convection and diffusion within this boundary layer. Okay. And the thickness of the boundary layer is basically determined from the condition that convection and diffusion are comparable. Okay. So, I will write down the momentum and energy equations in component form and scale the equations, okay, and examine how we can determine what is the boundary layer thickness and the transfer rate in the limit of high Grashof number. Okay. So, I will do this only for a 2-dimensional transport where there are variations only in the x and y directions, assuming that there is no variation in the direction perpendicular to the plane, which is the z direction. So, in this particular case, I can write down the mass, momentum and energy conservation equations in a 2-dimensional x, y coordinate system as partial Vx by partial x plus partial Vz by partial z is equal to 0, okay, and Vx partial Vx by partial x plus Vz partial Vx by partial z is equal to minus partial p by partial x plus 1 by Grashof to the half partial square Vx by partial x square plus partial square Vx by partial z square plus T into Gx, where Gx is the component of the gravitational force in the x direction. Okay. And similarly, the energy balance equation is Vx partial T by partial x I should write the z momentum conservation first. Let me just write that. So, these are the two components of the momentum balance equation, and finally, I have the energy balance equation V dot grad T. Okay. So, this is the energy balance equation. Okay. And as I just told you, when GR is large compared to 1, when the Grashof number is large compared to 1, these diffusion terms appear to be much smaller than the convection terms. Okay. However, if you neglect convection altogether, then there is no there is no I am sorry, if you neglect diffusion altogether, then it will just tell you that in the case of temperature, for example, the temperature is a constant along streamlines. And in that case, there is no way to satisfy the boundary conditions. The boundary conditions can be satisfied only if we postulate that there is the thin boundary layer close to the surface, whose thickness decreases to 0 as Grashof number goes to infinity, in such a way that convection and diffusion are comparable in this region. Okay. So, basically we will be considering the limit, the Grashof number per half is large, and the Prandtl number times the Grashof number per half is large. So, in this limit we can use boundary layer theory in order to determine what is the thickness of the boundary layer within which convection and diffusion are comparable. So, for the configuration that we had of characteristic dimension LC, T is equal to T naught, and T is equal to T infinity far away. We expect the effect of diffusion to be restricted to a thin region close to the surface in the limit of high Grashof number, close to the surface in the limit of high Grashof number, where convection and diffusion are comparable. If the thickness of this layer, which I will call as, I have called it as delta star, delta star times LC, is the thickness of this layer. That is, delta star is the boundary layer thickness divided by the characteristic length. If the thickness of this layer is delta star times LC, where delta star is much smaller than 1, then I can analyze the flow in a 2-dimensional coordinate system, which is defined locally at the surface. At each location, I can use a 2-dimensional coordinate system, which is defined locally at the surface. With cross stream distance z perpendicular to the surface and streamwise distance x along the surface. And within this region, I can scale the cross stream coordinate by delta star times LC and get a new scaling for the cross stream direction. Z plus is equal to z by delta star times LC. So, I will use this new scaling to rescale my equations. I will use this new scaling to rescale my equations and then determine the value of delta star in such a way that convection and diffusion are comparable within this boundary layer. I will continue this analysis in the next lecture. I will see you then.